Ladies and gentlemen, welcome to day 2 of XPANSE. So we've just had a wonderful kickoff in the Imaginarium, and now we'd like to welcome you to our first panel of the day. So we're kicking off with quantum computing, hardware and software frontiers. I will be your host. My name is Nicole Morgan. I'm a consultant at McKinsey Company, and with me joining us live here we have Nir and Leandro. And I will dive right in and let you guys introduce yourselves, and then we can dive into all the topics. And as we go, I think one of the beauties of the fireside chat is that you can join in. So when you have questions, please raise your hands, because we'd love you to be a part of this. This is how often do we get to pause in our day today and sit down and really think about the fascinating science and cutting edge technologies in quantum? So leverage the wonderful people we have with us today to your advantage. So without further ado, over to you, Leandro.
Great. Can we sit down?
Yeah, let's do it. Yeah.
So my name is Leandro Aolita. I am the Executive Director of the Quantum Algorithms Division at the Quantum Research Center in TII, the Technology Innovation Institute, here in Abu Dhabi. I have a background from quantum physics, theoretical quantum physics. Nowadays, what I do is somewhere between computer science and quantum physics. And I've been in the country for 3.5 years already, and I'm staying around.
Nice. And what brought you to Abu Dhabi?
Look, in my case, we have the leadership of Professor Jose Ignacio Latorre, who's the chief researcher of the Quantum Research Center. And we've known each other since I was in the beginning of my PhD. So many conferences and very long nights after conference dinners. And we have a great team of scientists at the Quantum Research Center. That's one of the main things that was for me a guarantee that I was coming to a great place for research. We have 6 divisions, 3 experimental ones and 3 theoretical ones. There's the Quantum Algorithms Division that I mentioned on the theory side. There's quantum physics and quantum middleware, but we also have experiments on quantum computing hardware, quantum sensing, and also quantum communication that they have set up the quantum key distribution demo there. So it's really a great place and for research and innovation, and the commitment and the let's say the initiative was very serious from the beginning, right? We have the privilege of, in a sense, so as you know, Technology Innovation Institute is an application-driven research institution, but quantum, as you know, needs to think a little bit longer term. The technology is just in an initial phase, in an experimental phase, and that, we have these causes that we need to have a very broad portfolio of research. We have some products like the QKD setup that is very advanced. And then we're also doing research on understanding the physics of superconducting qubit devices or designing more efficient quantum algorithms, which are very, very abstract and theoretical endeavors. So we have a very broad spectrum of activities. And we go from foundational problems on quantum algorithms and quantum hardware to proof of concept for end user applications in collaboration with industry, right? So we can tackle all those spectrum of things in a very nice environment with generous funding from the Abu Dhabi government. And
always helps.
Yeah, that helps. And an amazing pool of scientists, right? So currently at the Quantum Research Center, we're 95 people and growing, still counting, right?
Amazing. And Nir, what's your story? Tell everyone here.
Hi, so my name is Nir Minerbi, one of the co-founders and the CEO at Classicq. Classicq is a quantum computing software company based in Tel Aviv, in Israel. Also, we have presence in Tokyo, in New York, and Amsterdam. We established this company 4.5 years ago for a simple reason. It was quite clear that quantum hardware is going to be here somewhere in the not very long future, and yet no one could really program quantum computers. The development was done at a very, very low level. Assembly is much higher than what we had in quantum. So it was clear that the quantum software stack is needed. And this is what we do. For the past 4.5 years, we have building the Probably the most advanced quantum software stack, operating system, compiler, development environment, and it's used by many enterprises like BMW and Rolls-Royce, Toshiba, HSBC, many others, hundreds of academic institutions, and basically we are here for end users. You know, we need to enable quantum application development for the many amazing hardware modalities that are being built.
And so why in particular I'm really excited for this conversation is because we have the cross-cutting between the algorithms perspective and the hardware perspective. So within my world, at McKinsey, I focus on quantum computing hardware across, as Nir mentioned, the different qubit modalities. So whether that's superconducting qubits, neutral atoms, trapped ions, spin qubits, you name it. That's the world that I work in day to day. I'm also a physicist by background. So for me, what I would love to pick your brains on, as you're in the algorithms forefront of the field, what is the next leap from your perspective for both, not just the hardware side, but also the algorithm side?
Thanks. So from the hardware side, I think that the biggest challenge, let's say the big leap that we expect to have, is scaling up system sizes while maintaining gate fidelity. So let me speak for a minute what it means, this quantum error correction, why we need that, right? So as you may have heard, like quantum computing, the idea is to exploit these quantum features of microscopic systems to make them process information more efficiently. And these quantum features are things like entanglement and quantum superposition that are very fragile. That's why we don't see them every day on a macroscopic level, because these properties are very, very fragile. As soon as you put a quantum system in contact with some open reservoir or something like that, it loses its quantum properties. It becomes a classical device, and then you no longer have a quantum computer, you have just a classical computer, a very expensive one. So it's a challenge. We need to control microscopic systems, but we also want to have many of them, and we also need to be able to measure and read them out. And these are very contradictory requirements. You want them to be, to scale up while maintaining the isolation from the environment, but at the same time you need to control them and to measure them, and this is very hard to do. And so nowadays we have, for instance, the highest fidelity quantum computer platform available on the cloud. It has infidelities of 1 out of 1,000, so 10 to the minus 3, and we need to go beyond that. And it happens that it's not known with the currently known technology how to do it. Like the gate fidelities, they can maybe get to 10 to the minus 4, but beyond that, it's unrealistic with the currently known technology. And so the solution that we expect to have is to scale up and use something called quantum error correction. But this requires to use many more qubits, many more physical particles to encode the logical qubit. And then you need to do that, you need to increase the connectivity and the size of your system while at the same time maintaining very low error rates. And that's a challenge, and that's where we expect to have leaps in terms of scalability and scaling up the different platforms. And this is a question that can be addressed for each different platform differently. From the algorithmic side, from what I see is also big leaps in the theory of quantum error correction. This is a very multidisciplinary effort, right? You have the hardware efforts and scalability, and at the same time you have the efforts on the theory side, trying to make quantum error correction more efficient in the sense of requiring fewer physical qubits for each logical qubit that you want to do, right? And of course there are also things connected to understanding or like having more evidence of quantum exponential speedups for end-to-end, let's say, applications. So, essentially nowadays, the only algorithm that we know that we can prove, when I say end-to-end, means like you give me a number or you give me the task and written in some classical computer code, and I upload that into a quantum system and run a quantum computation, and then I give you back the result. That's the end-to-end cycle. And the only problem, or maybe one of the few problems for which we know that there's an exponential quantum speedup, is essentially factoring. It's the original Shor algorithm, right? So we go back.
Holy Grail.
We go back to the Holy Grail, right? So there's lots of evidence in terms of quantum exponential speedups for chemistry applications, for machine learning, and these centers also in finance, and there are many things. But they assume that we can do certain things with quantum hardware. That is still not fully clear that we can do it, right? So there's also leaps that we need to have on the quantum algorithm side to really understanding if we can have more quantum exponential speedups in an end-to-end sense.
And maybe just to set the scene a little before Nir, I'd love to get your perspective, as I think you're really closest to the end use cases and the kind of commercial end customers. But I think just to set the scene for where we are now in terms of quantum. So we don't have a quantum computer today that can really do the wonderful things that we know it can one day. We're still waiting for whether that'll be in the next 5, 10 years. I don't have a crystal ball. Sadly, I don't think you guys do either. But the key milestones that we're looking for. So the first, let's say, interesting use cases from a research perspective, that milestone is the 100 logical qubit milestone. And I mean, this is, controversial, but I'm simplifying for the sake of conversation. And then the next milestone would be 1,000 logical qubits, and that's where things should get really exciting from an end use case perspective in terms of the commercial world. So as you already mentioned, Nir, whether it's banking with HSBC or automotive, BMW, whoever it may be, that's the milestone where things start to commercially, you see the results that we're all, been working for, that you've dedicated your lives to. And so for me, one thing that is interesting is what is the intersection of algorithms today while we're still at this nascent stage from a hardware perspective? What does that look like now? And versus how do you think that's going to evolve in the next 5 years? Because we're having announcements, every couple months, crazy ones. Yesterday, I think we had an announcement from Microsoft and Atom Computing, I'm not sure if you all saw, of 24 logical qubits. I haven't checked the fidelity of those logical qubits, but either way, it's a big announcement for the quantum world. So Nir, over to you. How do you see the short term and the long term in terms of the intersection?
Sure. I think it's, if you ask someone at the 50s, what would be the killer application of a computer with billions of transistors, the answer would have been a really good calculator, probably not ChatGPT. So I think in quantum, we are in quite a good position because much before the hardware is here, literally with pen and paper, amazing algorithms were discovered, right? At the 80s, 90s, and in the last few years. So the motivation is here. We know that when, a fully scaled up quantum computer will be here, it's really going to be game changer. But on the other hand, only when the machine is here, many more applications could be discovered, many more heuristics, like AI, machine learning. It's not like usually mathematically proved. It's heuristics, good ones. So I think it's going to be much more exciting even than we anticipate today. And from the software perspective, from the software stack perspective, what needed to be done is to allow as many end users to develop applications for these machines. Because eventually, if you oversample this ecosystem every couple of months, yes, there are announcements, but it's slow progress. It will take some time. Yet, if you think, 2, 3, 5, 7, 10 years from now, the machines will be here, right? Because someone will deliver them, whether it's IBM or Google or Microsoft, or TII, or the government of Japan, or some academia. I don't know. I don't care. Don't tell anyone. It will be here. And then end users will be able to develop software, to program them, and to really find some amazing applications. So this is kind of the intersection from my perspective.
And I think that's a really important call to action because this is something we also really see on the McKinsey side. So when we serve end users, a lot of the time we get the question of, quantum, why now? What can I do with it? And fair question, but it's in terms of being ready for when it comes. Because, one of my good colleagues who's probably somewhere here, Henning Stoller, he serves banks a lot. And, banks are still undergoing digital transformations from legacy code in the 70s, 80s, and they're nowhere near, and the major players, right, on using the best cutting edge classical computing hardware, software that we have available to us today. So let alone make the leap to be quantum ready. So yes, today the bottleneck might be the hardware and the computer itself. We don't have it yet. It would be really great if we could have that one day, like you said. Whoever makes it, fantastic. But taking action now is really important, because there's a huge gap from the end user side to be ready for when that wonderful Q day, or whatever we want to call it, comes. And so maybe from your perspective, Nir, could you elaborate what would kind of be, if you could have a panel of the CTOs and CXOs of the end users, which, I mean, a lot of us in the room today, what would be your ask or your call to action?
Start small. I don't think you need to initiate a huge quantum activity, but if you take 2, 3, 5, 10 domain experts from your company, they don't have to be quantum experts. You dedicate them to learning quantum algorithms, quantum programming, to explore this ecosystem, to understand how to access a quantum computer, how to program it, what's a quantum cloud, and so on. So in 6 months, your organization will be much, ready, or at least understand what it's all about. And then you can start build assets. Assets are algorithms, knowledge within the organizations, working with different business units to understand their hard computational problems. And eventually it will come. Some of the organizations we work with, Rolls-Royce is a nice example. They work pretty much on the same algorithm, same CFD simulation algorithm for several years now, because it takes time. It takes time to make an organization ready. Even from an IT perspective, it takes time to develop these algorithms, to develop the team. So start now, start small. Don't need to start big, but do it now. I think it's a good timing. The ecosystem is advanced enough, and I think at this stage, it will be a much bigger story if quantum won't be here in a few years, rather than just, see it here in production in the next 5 to 7 years, not more than that probably.
And maybe could you elaborate, so in terms of Classicq in particular, how do you help end users? So what exactly, tell us here for anyone who might not know, how does Classicq bridge this gap? What does your service offer?
Sure, so we have built a platform that makes it easy to develop quantum software. It makes it easy to translate business problems like drug discovery or portfolio optimization or CFD or AI problems into quantum programming, and it allows domain experts who are not quantum experts, of course, also quantum experts, to do that very efficiently. So we work with these end users to train them, to train their teams, and to make them capable in developing a quantum code, cross-compile it to different hardware modalities, so they don't need to bet on the winner in the hardware race. And it's quite easy, relatively,
And I mean, we've had a lot of fun with the platform, right? With how easy it is to use, which I think is a big key unlock in terms of making quantum accessible, right? Because it's at its core, it's always going to be fundamentally very scientific and very hard to make it accessible to the broader public. So I think it's really wonderful that the work that you're doing that help bridge that knowledge gap to make it accessible to more people. And Leandro, so maybe to you, from the algorithms perspective, what is the kind of the thing that excites you most that you're working on with your team that is the next kind of milestone that you're working towards?
Thanks. So one thing that I'm very interested is coming back to the first question is to how to make algorithms more efficient and how to make use of simpler subroutines in such a way so as to simplify the quantum requirements, the requirements on quantum hardware.
The number of logical qubits, for example, to run a specific
the number
algorithm.
of logical qubits and also the number of operations that you have to apply, because that's also an important thing. People talk about the number of qubits or the number of logical qubits. The truth is that when we speak about a logical qubit, what we're meaning is actually some encoding that encodes a logical qubit with some error rate. So, and again, this gets technical, but the reason why it gets technical is because in order for you to implement circuits and to go to end-user applications, you need to have not only enough number of logical qubits, but also to apply a certain number of logical operations on them. If each logical operation has a probability of failing, as you accumulate, you act in more and more and more operations, at some point you will have errors, and then these errors are more likely the bigger the size of the system, right? The bigger the size of the circuit. And so a big question in quantum algorithms is how to make them more efficient, right? Like how can we get the same end user application, at least in theory? How can we develop another technique that solves the same problem, but using, let's say, 10 times the circuit size as the original proposal, or maybe 100 times less, right? And sometimes you need to bring innovative ideas that mix classical and quantum algorithms. And in fact, this is maybe going to be the most likely situation. It's not that quantum computers alone are going to solve all the algorithmic pipeline of a computational fluid dynamics application or a chemistry. You will have these situations where you have high-performance computing devices, where you will have certain tasks, certain subroutines being solved by a classical, like a CPU, and other things being solved on a GPU, and certain subroutines, the most valuable ones from the quantum perspective, will be solved by some quantum hardware. And the idea is now to try to remove the necessity of the quantum hardware for as much as possible from the entire algorithmic pipeline, and leave only the quantum hardware for a precious subroutine where you really need to have a speed up on quantum, right? And these are the so-called hybrid classical quantum algorithms. There are heuristics, as Nir was mentioning. There are also things that you can prove. You can, for instance, introduce classical randomness into the recipe, and with the help of randomness, you can reduce the circuit sizes involved at the expenses of maybe having to pay the price of a larger statistical complexity. This means more and more repetitions. So you run a smaller quantum circuit, but you run it more times, and then you do some classical post-processing. So these are all tricks that involve knowledge of computer science, mathematics, engineer, and of course quantum physics to try to, again, bring up solutions to end-user applications with fewer requirements on quantum hardware. There's a name that people have adopted for that research activity. It's called early fault-tolerant quantum algorithms. So people are doing now research on developing quantum algorithms that will be specially tailored to the first generation of fault-tolerant machines, those that have a limited number of logical qubits, and where each logical qubit is not perfect, meaning that you can apply a number of logical operations on it, but this number is limited, right? And so what can we do with these small initial quantum resources? That's one of the questions to which I like to put more passion nowadays. Of course, there's a big race on quantum error correction codes. There have been lots of advances in the last couple of years, both in the theory and experimental side. And then something interesting, maybe also connected to end-user applications and clients. The study of quantum algorithms is not just like a language, like a different language. So we have quantum software. This is crucial because we need to develop the whole stack of things from the high levels of abstraction to the actual pulses that run the machines. But in the end, you end up looking at problems from a totally different perspective. And this sometimes gives, so developing quantum algorithms really forces you to think in a different way, in a different computational way. And this sometimes sparks ideas that lead also to new solutions that can be implemented with classical hardware. So like CPUs and GPUs, as I was mentioning, there's a big activity in our quantum algorithms division, which are actually they're not devoted to studying quantum algorithms themselves, but study what people call quantum-inspired algorithms. And so, again, by looking at these problems with this different perspective of quantum algorithms, sometimes you get ideas and techniques that, a variant of which can be implemented with a GPU or a CPU, and that leads to new classical algorithms, a new generation of classical algorithms that sometimes give some speedups. Maybe not the precious exponential speedups that we're talking about, but some significant speedup. If you have an operation of billions, if you have a solution of 1 or 2% better quality, then that's a lot, right? So,
yeah.
So this is an interesting thing, right? And this allows us also to speak to industry today, because we are doing proof of concepts about quantum algorithms in the future, but at the same time trying to develop things, solutions that one can implement nowadays, right? So this is another exciting thing that we're looking at.
Amazing. Then one final opportunity. If there's any questions on your mind, now is your chance. Okay, wow, okay, all sorts. Then, yeah, let's start with you.
Hi, I work at NYU Abu Dhabi, and there is an interest from our faculty to actually purchase a quantum computer at the cryogenic level with the illusion refrigerator. And I was wondering how an institution like this, not a bank or a big corporation, can also invest into quantum computing and start developing its own hardware, perhaps.
So, I mean, it's an interesting question, and then feel free to add, but I think usually it's a case at this stage, if it's a research institution, we often see governments making those investments at this stage, because, I mean, both from a data sovereignty perspective and an intellectual property sovereignty perspective, but also just in terms of the sheer funding required for quantum computers, that's usually the way we see it this day. But, yeah.
So maybe I can add. I know people at NYU AD. I know that they also have a spin Q 2-qubit device, but that's for educational purposes, right? But I think that your question goes more towards like developing, like R&D uses, right? Of course, nowadays we have providers of quantum hardware. These machines are still prototypes. This is not. And they're not easy. That's why we have quantum software companies, because they're not so easy to use, right? I would say that in the future you won't be required to have a PhD in quantum to use them, because there are companies that will there are companies that will make your life easier in terms of programming. But even if you know how to, let's say, use them. It's a delicate decision, because it depends on on managing expectations, right? If you really just want to do R&D and learn what it means to acquire data from a quantum device, to understand what are the sources of noise of a quantum device, then I think it's a good decision to spend money from a university to acquire this type of machines. Then you will ask me which one, and that's a totally different discussion.
Yeah, how many hours do you have?
Yeah, but you have to be aware that these machines are still not there in terms of solving useful problems, right? So I think that's as much as I can say. Maybe you want to add something there.
Yeah, from a practical perspective, I think there are hundreds of quantum computers available via the cloud. You can access them, you can try them, and you need a good reason to actually buy a quantum computer today. Many do it right away, and you can learn from many national quantum programs. Japan has just acquired several quantum computers for hundreds of millions of dollars, which is a fine decision as a country. But as a research institute, I think there is much you could do without buying a machine. And yeah, I think at some point it definitely, when the winners are set, you will need to have a machine on site, but maybe it's not yet the time.
Maybe if I add just one thing that I forgot, because I think it's important, before buying a machine, investing on having top-notch specialists in a research institution. So being a research institution, I wouldn't advise to acquire expensive quantum hardware before you invest in setting up a top-notch team doing R&D in the topic, right? So I would advise not to buy that without having like a strong in-house team first, kind of managing that.
And super quickly, because I can see we're over time, final question from over here.
Hi, thank you for the panel. As I get it, classical and quantum are merging. So how strong is the case to have a pure quantum computer in 10 years' time? How will it look like?
So I think I can kick us off here, and we'll keep it brief because I can see we need to hand over to the next team. But I don't think quantum will ever replace classical. Quantum is only useful for very specific types of problems. So you're always going to have classical computing in its sheer force. But I mean, it's the hybrid for when you can split out a problem into its quantum mathematically piece by nature and then do the rest of the processing on classical, then you really get the best of both worlds. And maybe about the hybrid between quantum and classical, would you like to add?
I definitely agree. There's no case in having a only quantum computer. You don't want to. You're not going to, even if you have a fault tolerant large scale quantum computer, you're not going to use that to answer emails, for instance, right? Like you definitely want to save that. People are thinking of like high performance computer centers where you will have like clusters of CPUs, GPUs, and QPUs working all in tandem, right? So I think that's where we're moving to. Yeah.
A really nice hybrid, yeah. Super. Nir, anything to add?
No, I agree with everything.
Beautiful. Then thank you for a wonderful audience. Have a wonderful rest of your time at XPANSE and see you around.